Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 26, 2026, about 6 days ago. It introduces a comprehensive new framework called Auto-Eval that can verify source authenticity with over 99% accuracy, ensuring we know if a robot is acting autonomously or just being teleoperated. The paper is titled, Trustworthy Evaluation of Robotic Manipulation, a New Benchmark and Auto-Eval Methods. And as we'll see later, the implications for detecting unsafe but technically successful behaviors are really significant. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core motivation, termed the crisis of evaluation credibility. The top left panel, labeled Gap 1, shows how current binary metrics fail to distinguish between jerky, unsafe motions, and smooth execution, since both are marked as successes. Beside it, Gap 2 highlights source ambiguity, asking if a demo is truly autonomous or just a hidden human teleoperator. The bottom section maps out the solution, combining the Eval-Actions benchmark with the Auto-Eval architecture. On the right, the green box shows Auto-Eval achieving over 99% accuracy in source verification, far outpacing the standard baseline in the red box. Alright, following up on that motivation, Table 1 compares existing datasets with the new Eval-Actions benchmark. Most prior datasets, listed in the top rows like OpenX embodiment, focus purely on training, so they maximize raw trajectory counts but lack detailed annotations. In contrast, the bottom row shows Eval-Actions is explicitly designed for evaluation. You can see under the diagnostic annotations section that it uniquely provides failure scenarios, quality scoring, and chain-of-thought reasoning. Finally, the collection column highlights another key difference. It mixes human teleoperation with policy-generated data to test source authenticity. So, having seen the comparison in Table 1, Figure 2 now visualizes the actual structure of the Eval-Actions benchmark. On the left, the grid displays the diversity of tasks, ranging from simple single-arm interactions to complex bimanual coordination. The middle section is particularly telling. It breaks down a throwaway trash case study with 3 different outcomes. Notice the bottom example. The robot technically succeeds, but the annotation highlights that the motion is very jerky and involves a collision, revealing it as a policy-generated behavior rather than a human one. Finally, the panel on the right shows the rich data available for every episode, including RGB and depth streams, action trajectories, and multidimensional quality metrics. Well, now that we understand the data, Figure 5 lays out the architecture designed to process it. This diagram shows the Auto-Eval framework split into 2 specialized branches that handle the video input on the left. The top section, called Auto-Eval-S, focuses on efficient scoring. It uses a spatio-temporal aggregation strategy to compress video frames into visual tokens, which a fine-tuned model then uses to predict action quality, success, and source authenticity. In contrast, the bottom branch, Auto-Eval-P, is built for deeper reasoning. It employs a policy model to generate multiple chain-of-thought paths, denoted by think tokens, and optimizes them using group relative policy optimization to ensure the logic aligns with the final score. Okay, Figure 5 explained the how, and now Figure 6 demonstrates the why with a qualitative comparison. The top section evaluates a bowl stacking task, where the robot exhibits a subtle motion defect called duplicate crawling, highlighted by the red circles. Auto-Eval-S correctly identifies this glitch and lowers the score to 5, whereas the baseline model misses it entirely. Then in the bottom towel folding example, the robot drops the object during handover. The baseline QN versus L hallucinates a seamless transfer, but Auto-Eval-P accurately spots the failure in its reasoning and penalizes the score. While the previous figure showed specific examples, Table 2 now provides the quantitative evidence across the full benchmark. The first row reveals a critical finding. Without supervised fine-tuning, standard models like Intern versus L have a score correlation of just 0.01, meaning they are effectively guessing. In stark contrast, the bottom shaded rows show that Auto-Eval-S achieves a correlation of 0.84 under the rank-guided protocol. Furthermore, looking at the source prediction columns on the far right, the method identifies policy-generated videos with 99.6% accuracy. So, while the previous table showed the main results, Table 3 pushes further by testing generalization on a completely different robot, the Franca embodiment. Even with this shift in visual appearance and kinematics, Auto-Eval-S maintains strong performance. Under the rank-guided setting, specifically, it achieves a correlation of 0.75 and predicts source authenticity with 90% accuracy. The more complex Auto-Eval-P model sees a moderate drop to 0.54, but overall, these numbers confirm the framework isn't just memorizing one robot's dynamics. Wrapping up, 2 takeaways stand out. Binary success rates hide dangerous behaviors, and standard models fail at robotic evaluation without specific fine-tuning. By solving this, the Auto-Eval framework establishes a new standard for verifying that robots are both safe and genuinely autonomous. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.